Okay, good morning, ladies and gentlemen, and welcome back to another episode of Cyber Talks. And today I have the honor and privilege to have with us Professor Sotiris Ioannidis, Associate Professor at the School of Electrical and Computer Engineering of the Technical University of Crete, TUC. Professor Ioannidis received a Bachelor in Science degree in Mathematics and a Master in Science degree in Computer Science from the University of Greece in 1994 and 1996, respectively. In 1998, he received a Master in Science degree in Computer Science from the University of Rochester, and in 2005, he received his PhD from the University of Pennsylvania. Professor Ioannidis held a research scholar position at the Stevens Institute of Technology until 2007, and the research director at the Foundation for Research and Technology, HELAS, 4th until 2020. He is currently an associate professor at the School of Electrical and Computer Engineering of the Technical University of Crete, TUC. He has been a member of the ENISA advisory group since 2017 and a member of the National Infrastructure for Research and Technology, GRNET, Advisory Committee. He is also chairman of the Committee of Ethics and Deontology of Research of 4th and a member of the Advisory Committee of National Infrastructures of Research and Technology. His research interests are in the area of system and network security, security policy, privacy, and high-speed networks. Professor Ioannidis has authored more than 200 publications in international conferences and journals, as well as book chapters, and has both chaired and served on numerous program committees in prestigious conferences, such as ACMCCS and IEEE SNP. Professor Ioannidis is a Marie Curie Fellow and has participated in numerous international and European projects. He has been the PI of 40 European, national, and DARPA projects, attracting in excess of 12 million euro for his organization, and has been project coordinator in 14 of them. Currently, Professor Ioannidis is the deputy coordinator of one of 4 EU cybersecurity pilots founded by EU Horizon 2020 program and Concordia project. So, good morning, Professor Ioannidis, and thank you for being here with us. And I'll give you, of course, the host privilege and yeah, okay.
It seems we're losing our connection.
Yeah, you have now the host privilege, and the floor is yours, Professor Ioannidis.
Can you hear me?
Yeah, and the lecture of Professor Ioannidis will be on designing hardware systems for security and high performance. The floor is yours, Professor.
So, thank you, Tal, for your kind words and your invitation. Let me see how I can share my screen now. Okay, so hopefully you can see the screen. Let me maximize. Is it okay?
Yeah, great.
Right. So again, thank you for the kind invitation. It's an honor to be able to give a lecture here, and I'm hopeful that this is gonna be interesting and some people and help them understand some things about security and designing security inside the processor. I know you initially asked me for a more high-level presentation, and then I said, well, maybe we can do something more technical, and you're kind enough to permit me to go into something that's more hardcore, let's call it. Hopefully it's going to be interesting to your audience and provide some contrast to more high-level talks. But anyway, being close to the system and the hardware is, as I said, close to my heart, so I enjoy technical presentations more than high-level ones. So apologies for this, and I'm glad you accepted.
No, no, no.
So today, in the next 45 minutes or so, I'll talk about some work that we've been doing over the last few years with my colleagues and my students on hardware security. How do you exploit hardware to build more security into systems? So how do you enhance your hardware security features? The idea and the motivation behind this was actually fairly straightforward. We've been pushing functionality down the stack, so from the application to the OS, the kernel, and the hardware over the since the beginning. So the question is, what sort of things do we actually want to see materialize inside the CPU in the future? And there are numerous advantages to pushing things down the stack. Yes, we understand that abstraction and programmability of high level things is great, but there's some advantages to pushing things down the stack. So first and foremost is performance. If you build something in hardware, you gain performance. It just runs faster because you have specialized circuitry that does the operation that you want. So that's one big advantage. So if there is functionality that you want to invoke over and over and over again, specializing it and building it in hardware makes sense. The other advantage of pushing things down the stack onto the hardware is what we call transparency of functionality. So it's a well-defined operation, a well-defined instruction, let's call it, that you can invoke and do the work that you want accomplished. Now, when you have defined this functionality or this set of functions that you build into your hardware, this has the added bonus of simplifying your software. So instead of having to implement, maybe in software libraries or in user code, every time security features, in our case, that you want to see, you'd simply invoke some instruction or some set of instructions that are already built in to your CPU, and they provide exactly the functionality you want. So lastly, the other thing that you gain is energy efficiency. So instead of having a lot of user level software running software instructions, implementing the functionality that you want, there's a much more energy efficient implementation inside the CPU, and especially in our days where battery is important, in our cell phones, for example, and our other mobile devices, or maybe sensors that we deploy out there, energy consumption is probably the number one highest priority that you can have. So this is the kind of motivation behind our work. So the question is, what sort of functionality would we like to push down onto the hardware, onto the CPU, to increase security? Now, of course, this push is not something that is new. We've been doing it over the last 40 years by pushing a number of different features onto the hardware. The simplest example that probably most people are familiar with is memory protection. You have this mechanisms inside your processor to provide specific types of protection in memory that you use. So you can mark memory as read-only or execute-only or combinations. So this is a feature that increases robustness, increases security, and it's a feature that now everyone's familiar with and everyone finds it quite useful. Of course, there are tons of other features, things like rings, protection rings. So you may have different privileges depending on what sort of protection numerous rings with different levels of protection. So that's another feature that it's handy to implement in hardware. Hardware virtualization, it's another thing. It became huge in the last 20 or so years, especially with VMware and other companies that pushed it. Now modern processors have the hardware in them to support virtualization hardware. Yes, old hardware back 40 years ago did have these features, but commodity processors did not. But the people saw the advantages of virtualization, and now modern processors, commodity processors, support this. And there are a number of other security features and security extensions that have been implemented over the years. For example, last branch recording, a feature that was there for let's say debugging or performance, it still can be used for security purposes. Software guard extensions, another feature that we saw in Intel processors that create these secure containers for secure execution inside the processor, very similar to ARM's trust zone, and also TPMs, trusted platform modules, which make sure that you have some cryptographic operations to make sure that your system bootstraps from a secure state, and another functionality. So there is a continuum of functionality that finds its way from ideas and from software down the stack onto the hardware, and that's a good thing, at least in my view. Now, what we looked into, and I'm only going to be talking about ISR in this talk because I don't think I have infinite time. So I'm just going to be focusing on one technique that we worked on, although we worked on others as well, and specifically instruction set randomization. So again, this is a technical talk, but I'm not going to go into all the nitty-gritty of everything. I want people to get the feel of what the problem is about and what the solution is. The problem that ISR tries to solve is the problem of injection of malicious instructions into a running program. So you have your standard, process running in a system, maybe a web server, it could be whatever, and somehow an adversary, an attacker, manages to send malicious instructions into this running program, maybe via a buffer overflow. It's not important right now, and hijack the execution of this program. So this is the high-level description of the problem. So how do you stop that? Of course, there are a number of solutions that try to protect running programs from these types of attacks, and I'm not going to be discussing all of them. I'm just going to be focusing on the instruction set randomization solution. So the solution of ISR is to randomize the instructions of the program and of the processor for every execution of this program. And you'll see in a couple of slides what this actually means. Before I go into how this actually works, very quick reminder of how this injection works. So typically we have this box here, which is the abstraction of a running program, or a process as we call it. So this can be, for example, your web server. And inside this box, you have your code, you have your data, you have all sorts of things that are important for the execution of this program, this, say, web server. And specifically, there may be a chunk of memory, a buffer, which is vulnerable to this code injection attack. So the attacker will try to inject their code into this buffer. And the attacker will overwrite this buffer with their own instructions. So instructions coming from an attacker across the world find their way into the running program that, in our example, could be a web server.
May I have a question, please?
Yeah, of course.
Do you include in those kind of attack also SQL injection?
Yeah, you can have code injection attacks in SQL. We call them SQL injection attacks. In our example, in this talk, I'm talking about attacks that attack binaries. So the lowest level that you can possibly attack. But you can have code injection attacks at higher levels. And there are solutions for that as well. And they're actually equivalent randomization of instructions of SQL to counter these attacks. So there's also randomization defenses for SQL. Actually, in I don't know if it was the first paper in this or the second paper, when they proposed this method, the abstraction of the defense, not the actual implementation in hardware, which we actually did. One of their working examples was, I believe, SQL. So instead of randomizing binaries and, let's say, x86 instructions, they randomized the SQL instruction, because SQL has high-level instructions written in SQL. So I'm not sure if I answered your question.
No. Okay.
Okay, so the idea works at any level, but what we're focusing on is the lowest level possible, the hardware. Now, the way typically such an attack works is, of course, you insert your code and you overwrite either a return address or a function pointer, and that's how you can actually execute the malicious code. So that's how the attacker executes the malicious code. They just overwrite the pointer and they point back to wherever their own code lives inside this address space. So that is the kind of attack we're trying to protect. Again, the code in our example could be a binary because it's a memory space inside the process. But again, it could be an SQL execution and someone sent SQL instructions. So there are a number of solutions for this problem. And you have things like stack guard or point guard that try to protect the stack. So specific solutions protecting the memory space of the stack. You have solutions that do randomization of the entire address space, again in the layout of the process. And then it's harder for the attacker to guess where the return addresses are or where the pointers are. So there are solutions like that in software. And there are some also hardware solutions that rely on no execute bits that prevent code to be executed inside specific ranges of the address space. So there are solutions like that. But these solutions have been bypassed, and they're examples of how you can carry out these attacks. So the ISR solution, the instruction set randomization solution, tackles the problem at a much more basic level. It tackles at the level of the instruction. Now, when this was first proposed, there was no supporting hardware. So it was just a suggestion on design, and they did some emulation, and they also showed how an ISR solution would apply, as you said, to SQL or other languages. Our solution here is, how do you build it in hardware? How do you change your processor, your actual processor? And we actually created such a processor and executed this defense, did this defense, and showed that it's actually efficient and it works. So how does the ISR solution work? One starts with the original executable. So vanilla program, you don't do anything to it. And you take this program and you pass it through a randomizer. So you take the instructions, you take the binary that has, add instructions and load instructions and what have you, And every such instruction has its own format. So add could be, I don't know, 0000111111, and maybe move is 111000. These are hard-coded in the processor, and there's Intel has a specification of the format of these instructions. So you take every instruction and you shuffle it, you randomize it, you encrypt it, and then you create another binary that is, if you look at it, it's garbage. It doesn't really have any instruction. If you went and you did commands like object dump or disassemble or whatever, it'll just produce garbage. Because these instructions are invalid and they won't make any sense. But in ISR, you take this binary that now is, but once it starts executed and these instructions are fetched inside the processor, there is the inverse module, the de-randomizer, that decrypts every instruction and then it executes it. So that's the mechanism. You had something that looked like garbage, you put it in memory, you load it inside the processor, you load every instruction inside the processor, and then you do the inverse operation and you decrypt it. You de-randomize it. So you essentially have a randomized processor that takes randomized instructions, sorry, and executes them. Now, let's assume that, animation was maybe too fast. Let's assume that we have the vulnerable buffer and the attacker sends in their exploit. So they know we're running on x86 because 90% of the world runs on x86, at least for desktops and servers. And they send in binary instructions that are written in x86, and they inject this code. So now this box, this process, has this randomized executable with a bunch of code from the attacker that is written in x86. And sure enough, it tries to jump, it tries to execute this code, it tries to return to the piece of code that is injected. And that straight x86 code is sent into the de-randomizer and it's decrypted. But once an actual regular instruction is decrypted, it's actually turned into garbage. So what happens is that the program crashes. So any attempt to inject x86 code or other binary code that is supposed to be running on this processor will actually fail. The only way to carry out this attack is to guess what the randomized executable looks like. And you can make this guess very, very difficult. So that is the idea of the instruction set randomization defense. You can take this entire thing and change it into SQL. You can have an SQL interpreter here that takes randomized SQL instructions, that de-randomizes and executes them. The attacker will send actual SQL instructions that are de-randomized, therefore turned into garbage, that are going to fail. So the solution applies to higher levels. Okay? Now, where did we stand before our work? The previous approach to this was solely based on either emulators. So you took a thing like Box and you changed the Box interpreter and you did this technique. Or you took a binary and you had some dynamic instrumentation toolkit that plugged into specific instructions, and once they were fetched or decrypted, once they were fetched or tried to execute them, you decrypted them, and then this whole thing run. However, this is a software approach, so either by emulating an entire processor or by taking exceptions at every instruction and doing the instrumentation and the de-randomization. Of course, this had extremely high overhead, so times 10, times 100. So that's not really a viable solution. The other thing is that the way that previous ISR implementations were actually carried out you didn't really protect the underlying kernel, so the OS of a system. They were based on completely static binary encryption of the executables. So potentially over multiple executions, you could possibly guess the key. So the vector that the attacker sent could be encrypted in a similar way, and the attack then would be carried normally. So there was no hardware implementation. So our work was about doing it in hardware, see what it takes to change the processor, not just say, oh, I'm going to be interpreting some instruction in a different way, but seeing exactly what happens to the pipeline, what happens to the memory, the cache, and all that stuff, and measure to see if in hardware it makes sense to build such a defense. So where does our approach stand compared to the previous solutions? Typically, your system stack looks like this. Again, it's abstracted. You have applications, you have the OS, and you have the hardware. So in previous solutions, what you did was you had a layer of this emulation. You run your executable in a box, for example, or dynamic instrumentation, and you had these encrypted applications running on top of the simulation layer. In our approach, we went down the stack, we modified the hardware to be able to execute these encrypted binaries. And we did a few modifications, very few modifications in the kernel so that the kernel itself will be protected and provide full transparency to everything above the kernel, all the user applications. So that is the main difference in terms of overall architecture. We try to be as transparent as possible to the user applications. We don't want anyone to start running things in emulators, doing patching, all that stuff. We don't want any of this. So this has, of course, a number of advantages. Very little runtime overhead, protection of the kernel itself, shared library support. So previous solutions did not support shared libraries because shared libraries are not part of the binary. They live outside the binary and they're fetched whenever they're needed. So there was no support for that. Everything had to be in a complete block of code in a static binary. We do transparent code encryption, and we tolerate these guessing attacks. So if the attacker has multiple tries to try different keys and encrypt things in a different way, in our solution, this is going to be very hard to do. So again, this is a slightly abstracted instruction pipeline. So to show you what happens when ISR runs and what needs to happen. So typically you start with an instruction fetch and you do an encryption or a decryption, sorry, of this instruction. So things must be decrypted before they go deep down the pipeline and they start executing, because if you start decoding the instruction and you haven't decrypted it, it's basically going to crash. So we had to add our support at the fetch phase. And you could place, and you do place the decryptor after the cache. So typically when you bring instructions from memory, they go into the cache, and then from the cache, they're being fetched onto the core of the CPU, and you're starting to process them, decoding them, etc. So we've placed our decryption unit after the instruction cache. So encrypted instructions come from memory, they're stored in the cache, and when you need to fetch them, you pass them through this decryption unit, and they're unencrypted, and you use a key to decrypt them. Now the key is, there's some logic in there to tell you exactly which key to use for each cache line and all that stuff, but this is not particularly important. the idea is that you fetch encrypted instructions inside your cache and you decode them. There is an alternate solution to place your decryption before the instruction cache. Keep in mind that at the end of the day, we want decrypted instructions to appear at the decode phase, because that's where you try to figure out what happens to the what instruction you want to execute. So you need to finish everything at the instruction fetch phase. Everything after that, you need to have a decoded instruction, otherwise the whole thing is going to fail. So one approach is the one I discussed. You place the decryption unit right before you do the fetch. And the other solution is to do the decryption before you send the data into the cache. So the cache stores unencrypted data. So these are the two design choices that we had of where to place the decryption unit. Now the question is, where is the right place to do it? In our solution, we selected to place and as you'll see in the follow-up slide, to place the decryptor before the instruction cache. And there are a few reasons why we opted for that solution. Mind you, both solutions would work. The advantage of putting things encrypted in the instruction cache is that if the attacker somehow manages to inject code in the cache, they will fail because the system expects encrypted instructions to be in the cache. Whereas if we place it before, if they somehow manage to place instructions inside the instruction cache, they'll carry on the attack. However, to our knowledge, this is something that they cannot do. I mean, there's no way, based on the architecture of the processor, to add instructions inside the instruction cache. However, there are a number of drawbacks if you opt for the solution of encrypted data in the cache. If you have it encrypted inside the cache, at every time you do a fetch, you'll need to do the decryption. And that adds some overhead in terms of time. And it also adds some overhead in terms of energy spent because you do more operations. However, if you place it before, you don't have this problem. You don't need to do it every time. This is important because typically we have loops in programs that go to the cache over and over and over again to get data. So you don't want to be decrypting the same instructions, sorry, not data, instructions. You don't want to be decrypting the same instructions over and over again. You want to do it once. So since there are no attacks that can inject codes in cache, and since you don't want to be spending the extra time decrypting the same instructions over and over, in our view, the right solution was to do it before the instruction cache. With that decide decision outside and done with it, let's go into a bit more of the details. How does this encryption work? The encryption is essentially this part here, where I say XOR. XOR is probably the simplest way to do encryption decryption or randomization de-randomization. You could implement more complex decryptors and encryptors, and we actually did that in our experiments, but let's start with a very simple example. So one path is like before, data comes in from memory, they go into this decryptor, which is just an XOR gate, nothing fancy. You don't need anything fancy, and things go unencrypted into the cache. Now, there is some added logic that we added to decide which key to use every time. So, as I said, we also are able to do kernel encryption with this and protect the kernel. So one of the keys is the key of the kernel. So every time you go in the kernel, you use this key. But you also need a set of other keys, one for every user application. and we added a new instruction to in the instruction set to load this key. So we need one key for the kernel and one key per process that you want to protect. And this is the logic and the registers that are responsible for that. That's all that logic does. So you can see it's actually very, very simple. We're talking about a multiplexer, a couple of registers, an XOR gate, and that's it. So the solution in hardware is actually very clean. Now, a bit more details about this. Of course, you can use longer keys. You don't have to have a 32-bit key. You can have a 128-bit key. And so you fetch instructions in blocks, and you put them in your cache in blocks. So again, you can use keys that are 128-bit long, and there's some addressing there to be done. Again, this is not particularly important. The point is that you can use longer keys than 32 bits. And also, as I said, you're not mandated to just use a simple XOR. You can use more complex encryption algorithms at this phase. You need the grid that use 160-bit keys, and there you need a few multiplexers to carry this out. But you can go as complex as you want. You could implement an entire AES algorithm here, for example, to really feel that you are doing hard encryption and strong encryption on the instructions. Again, it's up to you. You can go the very quick XOR route, maybe the intermediate route of a shuffling and transposition algorithm, or you can go full AES or whatever your favorite algorithm is, depending on how much time you want to spend or how much chip surface you want to spend. Now, there is some need to modify the process a bit to support this, because now the system needs to know that that there's encryption in the binary. Again, the details of the format is not important, but I just want to say that the shaded part is a part of the process that contains the instructions. We don't care about the data, just the instructions. And we added some metadata to point out that, okay, there is an encryption going on and there is a key somewhere, so that the system knows that we're talking about encrypted binaries. So we can run either regular binaries, don't do any encryption whatsoever, have it running normally. You might have encrypted binaries, but for those, you need to let the system know that, look, this is an encrypted binary, so it doesn't crash, basically. So some modifications, but this is supported. So you can extend this. You're allowed to add more metadata to explain to the loader of the operating system to what to load and where to load it. So that doesn't make things particularly more complex. It just adds another section, and that's valid. Now, if we use static keys, of course, just once before encryption, once you create the binary, once you create a new program to run, that could be susceptible to guessing attacks. Also, you have to encrypt all the necessary code for this inside this binary, so no shared library. So static binary encryption has advantages, but also has some disadvantages. In our system, we also built dynamic code encryption. This way, you can create random keys every time you load the program. So when you do the fork exec, let's say, you encrypt the binary once you load it, instead of having it statically encrypted on a disk. And then and that's why you need to modify the OS a bit, because you need the OS to be able to handle this. So every time that the kernel does a pageful, for example, and handles a chunk of data that contains code, it needs to know that this is actually encrypted, and so it can tell the hardware that this is encrypted. Please decrypt it. Now, this makes it much more robust in terms of guessing, because you can change the key at every execution. And it's more transparent, and you can use shared libraries, because every essential page, essentially every page that contains code can have its own key. So you can get code from shared libraries running inside your address space, and they can have their own keys, and the OS will know about that, will decrypt them properly. So much more practical in actual usage. There are some requirements that are not obvious, and one had to deal with them, and we encountered some of them as we're doing this work. There has to be clear separation of code and data. We're not talking about data at all. We're just looking at the code. We don't want the attacker to be able to add code that does whatever they want. So there has to be very clear separation of code and data. Modern, when you compile a program, often the compiler will put data and code together in a segment, maybe for optimizations, for its own reasons. It's not important to go down that path. And when we started doing this, we didn't pay attention to that, and we're getting crashes, and we're wondering what's going on. And we found out fairly quickly that the compiler was doing things. So you have to separate code and data in separate segments when you're doing the static binary encryption. When talking about dynamic encryption, again, at every page, you have to separate code from data. That is completely and utterly important. Now, some systems nowadays use self-modifying code or dynamic code generation, which is more tricky. Now, in these cases, we created a new system call, essentially, that allows you to, when new code is generated, because your program wants to do some optimization, you encrypt it on the fly. So we do have support even for self-modifying code. How does the OS handle this? Well, in this example, I have a static encrypted binary and an unmodified, and a couple of examples of an unmodified binary, and they can run side by side. It's not a problem. For the static ones, we already defined that the binary as a static encrypted binary, and there in the process table, we hold the keys of every binary, either statically encrypted or dynamically encrypted. And we have told the kernel which is static, which is dynamic, and the kernel knows all this information. Now, what happens when we start running? Again, this is an abstraction of the hardware on one end and the OS on the other end. So what happens is when you have the scheduler running, process A, so the scheduler said, okay, your process A, you're running now. Process B and C, you're in standby. Okay, wait. Inside the CPU, there's a register that holds the key for binary A, and of course the kernel key. And since you're running the program, the process A, the supervisor mode is 0, so you're running in user mode. So every time you're using user key A, once you are going to do a context switch, there's a trap, and the mode of the processor changes from 0 to 1. So once you trap and you go into the kernel, transparently, the hardware knows to now use the key of the kernel, and so that the kernel will not crash, and you can protect the kernel with encryption. And now the kernel does all the processing it needs to do, does the context switch, loads process B, sets process B as a running process, sets process A as a ready to run process. It sets the new key for process B, and then it returns from this exception, from this context switch, and it runs process B. Now you see that the key has changed, and the supervisor mode is 0. So everything is happening transparently to the user. They don't see anything. But the kernel needs to be modified just a slight bit to tell the hardware, change the keys. What happens at page faults? At page faults, we only need to check if we're running in dynamic mode to see whether the page that you fetch in is encrypted or not. And if you're running in encrypted mode, and I back here, I set up the information about who is static and who's dynamic. So now we know whether A or B or C is a dynamic or a static encrypted binary. So at page fault, we had to modify the page fault handler with this extra information to do the encrypted copy of the page onto the memory. So it takes a page that is not encrypted, it encrypts it, and now puts it in memory. So when it runs, it can get decrypted by the CPU. So again, full transparency to the user. Now, this was for user space. How do you handle the kernel? Well, the kernel is a special case, and we do it statically. We use a randomly generated key when you load up your OS, and you handle it essentially like a static binary, and that's it. Nothing special on that. This was all about the design. Now, how did we actually implement this? Because as I said in the beginning, we did this in hardware. Of course, we don't have a stamping process that that creates processors. So we have a processor specification, but we run it on FPGAs. For our example, we use the Leon 3 processor, which is essentially a soft core. It's a Spark processor. It's an actual processor. There's a, it could have been an Intel x86 if we had the specification. And we did all the modifications of the processor, of the hardware of the processor, and run it on a Xilinx FPGA. And we used a couple of versions of Linux for the modified kernel. So how do we do? First of all, we wanted to evaluate what is the cost that we have to pay in terms of space on the processor, on the chip. So Leon 3, that version of the Spark processor is it's a very simple processor, okay? And I'll tell you why that matters. And once you create the hardware, the binary file for the processor, the bit file, I believe it's called, you create a number of flip-flops and lookup tables that comprise this processor. And we had like almost 10,000 flip-flops and like 17,000 lookup tables. And this is the vanilla, no modifications. So what happens if you add the extra hardware? If you just use a simple XOR, the increase in hardware is of the order of 1%, less than 1%. So with spending 1% more surface area, you get all this extra security. If you go to higher key lengths, of course, this increases. And if you go to things like transposition, which is much more complex, it decreases even further. So if you added the AES there, this would be even higher. However, about a couple of minutes ago, I said Leon 3 is a very simple processor. So any additional hardware that you add is going to be a large percentage of the processor functionality. If we looked at modern processors that are much complex, much bigger, the percentile increase would be much smaller because they have huge caches, they have all sorts of complex instruction decoding, they have deep pipelines, they have all sorts of things that make it very, very complex and very, very big. Whereas our circuitry is going to be the same. It's going to be a much smaller fraction. So the numbers here for the more complex encryption techniques are sort of misleading in terms of how much space area you waste on security. But again, that's something that ultimately you need to make a decision. Do you want the extra die space on extra cache or extra security? But that's always the case with any optimization in the processor. So how about security? Does it add any security? Well, the answer is yes. We tried a number of exploits. So these are real programs that are real vulnerabilities that run out there in the wild. And there are different kinds of exploits. There are local exploits, remote exploits. stack-based exploits, BSS, heap-based exploits, kernel exploits, and every time our system defended, and the attacker was not able to take over the execution of the vulnerable program. Now, I talked about extra space on the die. I talked about whether it actually works or not. How about performance in terms of, does it take a long time to execute? So for this, we compared the totally unmodified Linux kernel running a binary, and we tested static encryption and dynamic encryption. So to see how much does it cost to go the completely simple route versus the completely dynamic route of dynamic code encryption. And for that, we used 3 different types of benchmarks. One is something that you test CPUs with, performance of CPUs with, so it's the CPU 06 benchmark suite. But we also wanted to test other workloads like an HTTP server, so a web server, or database. So we use HTTPD Lite and SQLite. So tests that focus on CPU, tests that focus on web traffic, tests that focus on databases. So we have a full suite of tests. So for the spec bench, in this graph, on the vertical axis, I show slowdown. So lower is better. Slowdown of 1 means you're as fast as not doing any modifications at all. And higher is worse. And on the horizontal axis, there's a number of benchmarks that are part of the spec suite. So things like GCC, bzip, and so on and so forth. It's not really important what they are. And we're testing the 3 cases of the totally unprotected system, the vanilla system, the vanilla processor, versus static encryption of binaries versus dynamic encryption of binaries. I think the first thing to note is that the assist execution, the assist processor, the modified processor, is very, very close to the vanilla execution. So within the margin of error. So it's not easy, it's not even measurable. In the worst case, assist as a whole imposes less than 1.5% slowdown. So you get all this protection against all these attacks, and essentially 1.5 impact on execution time. The other thing to note is that the dynamic encryption performs practically equally well to the static encryption. And that's quite important. And why is that? Why does this happen? Why does the static one and the dynamic one, remember, it does encryption at every page fold, and you need to change the kernel a bit to handle this. No, it does more work. But why does this happen? We went at every benchmark and we marked down how many page folds are attributed to data and how many are attributed to text. Text is the code that executes. Remember, we don't care about the data. We care about code. We care about what happens with the code. So all the overhead is related to the page folds that are related to code, so to text page folds. If you look at the numbers, the page folds per second for code is a lot lower than the page fold exceptions for data. And that's expected because you typically get your code in and you run it over and over and over again on different data. So that's expected. And in many cases, it's significantly less than one text page fold per second. So very, very low rate. And of course, as expected, the majority is data page fold, so times 10, times 100 more. So due to this fact, we only need to run the more complicated encryption, decryption parts of our modified OS only a fraction of the time. And keep in mind that the majority of the time is actually spent fetching the pages from disk or from memory or from wherever. So the actual cost of the encryption of the text pages is negligible. And maybe I can go back and you can clearly see that they're very close. And I believe there's one benchmark. Maybe it's, yeah. So GCC has probably the highest page faults per second, and probably that's the only one that you can actually see some difference. For all the other cases, it's within the error of margin. So this is good. This is good because you can do the dynamic solution that encompasses everything without having the extra cost. So that's about performance in completely CPU dominated programs. So what happens with the web? So you go on the web server and you get files. Again, similar graph, slow down on one axis, file size on the horizontal axis. So how much data you're fetching when you do a GET request. So when you visit the page. So higher slowdown is worse, and one is the baseline execution of the unmodified processor. So again, it's interesting to notice that less than 1% slowdown in download times in the worst case. The other thing to note, again, is dynamic encryption, again, performs very closely to the static encryption for the reasons that I mentioned before. When you do a page fault, the rate of text page faults is much lower than the rate of data page faults, and they typically happen when the first request happens. So in the first few milliseconds of the execution, then you get no page faults at all. So again, for the workload that focuses on web traffic, again, less than 1% overhead to go for the extra protection. And typically you want to protect your web server from such attacks, from remote code injection attacks. So let's go to the third case with database. Again, similar graph, slow down, so higher is worse. 1 is the baseline, and on the horizontal axis, instead of file sizes, now we have table insertions. Also, in the third case, less than 1% slowdown, both dynamic and static encryption cases. So it works also for databases. Again, databases is the other big thing that you want to protect. Even for small data sets, you may have multiple small insertions in the tables. Again, even there, the performance is quite good. Because maybe if you have lots of little insertions, you would expect more calls and more strain on the system. But even in small data sets, we're doing just fine. So I'm reaching the end now, and I'd like to sum up in the following way. We did the first hardware-assisted architecture of ISR. So the previous one was the recommendation of the proposal of such a system and emulation. But we actually did in hardware. We changed the real processor, and we measured it. And in all cases, we had less than 1% runtime overhead, and we had less than or close to 1% of space overhead in the very simple cases of XOR encryption. So it makes sense both in terms of space and in terms of time. This work focused on Spark v8. Our current work focuses on RISC-V, so RISC-V. This is the up-and-coming open source core, and we've been porting everything in the new course, and it seems to be gaining a lot of traction. So we're very optimistic that maybe in the they will include such solutions in the RISC-V processor. There's some other work that we're doing with RISC-V, again in hardware support for security called CFI, and there's also interest in including such hardware solutions in the specification of the processor. So that way, it can find its way on actual hardware, not simulated hardware in FPGA. The other important thing is that even in the dynamic case, due to the fact that we're talking about code and not data, where and data faults dominate the execution, things work very efficiently. It can be done transparently. It can support shared libraries, and you can generate random keys at each execution, so that you protect yourself against key guessing attacks. So you get this increased performance, increased security, and complete transparency. Now, just one note at the end, at least in my view and in our view, when we did this work, and we think that it's worth spending this extra chip area on security functionality. It's a worthy investment. It doesn't take up much space. It doesn't take much energy. It doesn't take up much time. I didn't present any energy measurements. I have them in other talks, but it would be just way too long. But we think that it's worth it. And history shows us that every time there was a suggestion to include a security feature in hardware, this paid off, be it non-execute bits, memory protection in general, virtualization, and so on and so forth. So we think that it's a worthy investment. You can find more information on my page, and you can follow me on Twitter if you want, where we post things that we think are interesting. And with this, if you have any further questions, I'll be happy to answer them.
Thank you very much, Professor Ioannidis, for this most interesting lecture and presentation. I have one question, with your permission, please. You spoke about measures of how we can encrypt and how can we defend ourselves and the hardware. And I have a question from the opposite side. Well, probably it's kind of another completely different lecture of yours, no doubt. But perhaps shortly, not to take more from your time, about attacks. I mean, what are current type of information security attacks or cyber, what we call cyber attacks against hardware? Okay, what are the main threats against hardware those days?
Okay, now you have to invite me for another talk.
That's what I said. Yeah.
Okay.
That I'm completely sure that it's completely another different lecture of yours. Yeah.
Okay.
Yeah,
okay. So maybe I'm gonna regret this, but I promise if you invite me, I'll give a talk about that.
I'll do it.
Oh, damn. You buy me a beer when this lockdown is settled with.
By the way, I was in Crete last year.
Yes. Obviously, and I'm sure you're coming next year as well. Assuming that we're going to have this.
Yeah. This year it was online, but I hope that next year it will be. Yeah. And 2019, pardon, it was. I've been there for something like 24 hours because it was in the gap between my lectures, my classes. But next year, gladly.
So to get back to the question after we discussed, beer and Crete and sun and lockdowns, we have been getting better and better at protecting assets, so software, hardware, etc. So the thing is that even though we're getting better, all the attacks still work. So we should not rest and say, okay, now we know how to defend against code injection attacks or control flow attacks or what have you, because we have invented these things. We have to remain vigilant about all these past attacks because they're still applicable. Now, the state-of-the-art attacks that you're seeing in hardware, these are side channel attacks. So how do you exploit unintended consequences in the design of caches or processors or whatever? And these attacks also are related to information leakage, which is, these are very, very hard problems to defend against due to their nature. The one thing I can say is that they're also hard to carry out. So yes, maybe in the lab, they work maybe with high accuracy, and you can carry out these guessing attacks and bit flipping attacks and all that. Yeah, and also they've been shown to work in the wild, but they're very niche attacks. And the fact that we're moving towards these more niche attacks gives me hope that our defenses are getting better. But these attacks are very hard to defend against, and there's a lot of work in building more robust hardware to defend against these side channel attacks. And there you have to waste probably some resources to do that. So again, it's a balance of, do you want to waste some hardware resource, some area on the chip to build in a way that's more robust to side channel attacks? You probably want to do that because we have all this chip area. So I think this is where we're heading in terms of security, more niche attacks that can still be devastating, however.
Okay, so now we have the topic for your next lecture and our next meeting. Well, not next week, but of course. Ethan, any question from your side?
No questions, but I would like to say that though I didn't follow all the technical details and all this stuff, it was really interesting to see how you talking about hardware security solutions, because it really changed my mind about this thing. And I always thought, in the web, in the applications, but hardware solutions is a new world, I think. So thank you very much for this interesting and profound lecture.
Thank you. I really did hope I didn't bore your audience. Again, this was a more technical talk. It could have been a lot more technical, I can tell you. The figures were abstracted a lot, but I think that I'll try to relay the ideas and the feeling behind the defenses, and hopefully show your audience that there are hidden things inside the processor that make our life more secure, and the less we see that, the better for 99.999 of us. Maybe the fraction of us that has to deal with it and build it and design it, yeah, it may make our life more difficult, but to me it's really important. If you hide these things under the rug, it simplifies the life of so many other people that need to build systems on top of that it's definitely worth the effort. You need to build on solid foundations. Remember, there's this race for the bottom. Whoever controls the lower layer, the lower layer wins, because they control everything above that. So you need to build solid, secure foundations in any system.
Very clever, and enlightening. Thank you, Professor Sotiris Ioannidis, Associate Professor at the School of Electrical and Computer Engineering of the Technical University of Crete, TUC, for this very interesting, not only interesting, but also, as Ethan said, it's enlightening. And we used to think of security at the level of the information, at the level of software, but your last phrase was a very enriching one, enlightening, that you need to secure your very basic layers. And thank you very much for this enriching talk and lecture about designing hardware system for security and high performance. Thank you very much, Professor. And of course, we will be glad to see you in another session. We have another topic.
Thank you very much for the invitation.
Thank you very much. Take care. Bye-bye. See you. Bye-bye.
Bye-bye.